Hey everybody, Dr. A here, and in this video we're going to be exploring another example of shear and moment functions. So let's go ahead and get started. In the given information, we're being asked to write the shear and moment functions for the compound beam. Now, looking at this diagram here, what we mean by a compound beam is one that has an internal hinge somewhere along its span, okay? So in this particular beam, at point A, we have a fixed connection. At point B, we have an internal hinge that we have labeled here. And then at point C, we have an external roller. Both of the two half spans of the compound beam are 5 feet each, and the span of BC is supporting a 0.2 KLF load. The other thing we want to notice about this particular problem is that we have two domains that we're going to have to do some calculations on. The first domain is from point A to point B, and that's going to be defined by the variable x1. The second domain is from point B to point C, defined by the variable x2. So as you already know, whenever you have multiple domains on a beam, you can define one x variable for the whole beam, and then add and subtract moment arms and distances accordingly, or you can define a new location variable every time there's an abrupt change along the length of the beam. And that's what we're going to illustrate in this example, is defining a new x variable every time there's an abrupt change in our system. And so the abrupt change here that we need to pay attention to is the fact that we have an internal hinge at B, and additionally we have that 0.2 KLF that initiates at point B and then spreads across to point C. Okay, so let's go ahead and get started. I'm going to write solution here. Now, if you remember from your knowledge of statics, whenever you have a compound beam, which again is made up of pin-connected members connected by this internal hinge, we need to solve for external reactions first, and in order to do that, we need to disassemble at that internal hinge B. So I'm going to write that down, disassemble at the internal hinge B. Now the reason why we have to do that is if you're not careful, if you look at this entire system, you may think to yourself, oh, I have 3 external reactions at the fixed connection and I have 1 reaction at C. It looks like I have 4 external reactions, and you may think you're stuck, but you're not stuck because we have to disassemble at that internal hinge B. So I'm going to disassemble, and I'm going to draw a free body diagram of the disassembled system. So I have an AY, an AX, and I have an MA on the left span. That's 5 feet long. And then I've disassembled at the internal hinge B. And on the right 5-foot span, which is also 5 feet long, I have that 0.2 KLF that is spread out over that span. And then at point C, I have a vertical reaction. Now, what's happening at this disassembled internal hinge? Well, remember, an internal hinge can support forces but no moments. So I can support a BY and a BX value. Now, on either side of the disassembled internal hinge, those forces BY and BX are going to be equal in magnitude but opposite in direction. So you have a BY on either side of the internal hinge, but notice they're pointing in opposite directions, and similarly the BXs are pointing in opposite directions, but they're equal in magnitude because ultimately that is the same point that's connecting both of these two pieces together. So where do we get started? Well, we're going to want to start our analysis with the left free body diagram. Okay, we need to start with the left free body diagram. The reason why we cannot start with the right free body diagram is why? Well, you think to yourself, see if you can think of it to yourself. Why can we not start with the left free body diagram? I'm going to tell you the answer. So you better pause the video if you want to keep thinking. The reason is because there are 5 unknown reactions in this left free body diagram. You have 3 external reactions at point A, and then you have Bx and By at the internal hinge B. So, and you only have 3 equilibrium equations that you can use. So you're not going to be able to do much with the left free body diagram at this stage. But the right free body diagram only has 3 external reactions, Cy, Bx, and By. So we're going to start by analyzing. I'm going to say analyze the left free body diagram, which is of BC. Okay, now let's make our lives easier. If you look really closely at BC, you notice that this is symmetrically loaded. So I'm going to make a note, since this is symmetrically loaded and its geometry is symmetric, we can say AY equals CY, and that just equals 0.2 KLF times 5 feet divided by 2. And so when we do that, we clearly get 0.5 kips reacting up for, I'm sorry, not AY, that's supposed to be BY. Points to you if you caught that. BY equals CY equals 0.5 kips reacting up. Okay, now if you have trouble seeing this, that's okay. All you need to do is write your equilibrium equations and solve for By and Cy by summing forces in the y direction and summing moments about one of those points and solving for the other one, okay? But by symmetry, it's 0.5 kips going up, and also by inspection, we can clearly see that Bx equals 0. Now, because we figured out By is 0.5 kips going up in the free body diagram of BC, we know that it is in fact pointing down in the free body diagram of AB. So we're going to say from free body diagram AB, which is the left free body diagram. Oh, I labeled something wrong here. Let's fix that. I said analyze the left free body diagram. Another 2 points if you caught that. That should have said right free body diagram. I guess I mixed up my left and my right too much still. So from the free body diagram of AB, which is on the left, we can now say AY is here, MA is here, AX is here, and then BY is 0.5 kips pointing down, and of course BX was 0 from earlier, and that is 5 feet long. And so clearly we can say by summing forces in the x direction, we see that AX is 0, and then hopefully you can look at this and just be able to tell that by inspection, or you can write some of this out. Summing forces in the y direction shows us that AY equals 0.5 kips reacting upwards, and by summing moments about point A, we can clearly see that the moment reaction at A is 2.5 kip feet reacting counterclockwise. So these are all of our external reactions along with Cy. Again, this is a compound beam from statics, so you should know a little bit about this already. If you're a little rusty on this, maybe pause the video, rewind it, and do some review on your own. So now I'm going to get to really what the point of this video is about, and that's writing our shear and moment functions. So we had 2 domains. I'm going to start with the first domain. I'm going to call it domain 1, and that is going to run from x1 going from 0 up to 5 feet, okay? Now I'm going to include my origin for x1, which was the fixed reaction, and I'm going to include all of the terms that are within that domain. So the 0.5 kips reaction at AY is there, and the 2.5 kip foot moment is present there. And then by method of sections, we made a cut here, and we see that we have a internal shear force V1 and an internal bending moment M1, and these are functions. These are still going to be functions of X1, okay? And so we're going to say sum of the forces in the Y direction on this free body diagram, and we can clearly see that V1 equals 0.5 kips, and it's pointing down. And we're going to say sum of the moments about the cut equals 0, and we can say 0.5 kips times X1 plus 2.5 kip feet and plus M1 equals 0. So we do some rearranging and we'll get M1 is 0.5 X1 minus 2.5, and collectively that's going to carry units of kip feet. So these are shear and moment functions on domain 1. Now we're going to do something very similar for domain 2. Domain 2. And domain 2 was defined by that x2 variable, as we can see from the original problem statement. So x2 is going to run from 0 up to 5 feet as well. But remember, that's a different 5 feet. That's not the same 5 feet as the first domain. This is the distance between point B and point C this time. So we're going to do method of sections again, and we're going to remember that this stage, it's all just regular method of sections. We're going to include everything to the left of the cut that we're making here. So we're making a cut somewhere here, and we have that internal hinge that we're cutting on the right side of. And so we're including everything all the way to the left, which also means we're including the 0.5 kips reaction from AY, the moment reaction, 2.5 kip feet, and we're cutting to the right of the internal hinge, which means there's going to be a little piece of this uniform distributed load 0.2 KLF. But we're not going to show it throughout the whole 5 feet. We're going to show it over a small distance called x2. And the left span entire 5 feet is going to show up there. So we can draw our loads. They're going to become visible here. Here's V2. Here is M2. And we can apply equilibrium equations to this free body diagram. We're going to say sum of the forces in the y direction equals 0. And we're going to say 0.5 kips minus 0.2 KLF times x2 minus V2 equals 0. Do some rearranging and we'll get V2 is minus 0.2 x2 plus 0.5 plus 0.5, and collectively this carries units of kips, and we're going to say sum of the moments about the cut equals 0, and we're going to write minus 0.5 kips. And what's that moment arm to the cut? Well, it's 5 feet plus x2, so we're going to say times 5 feet plus x2 plus 2.5 kip feet plus 0.2 KLF times x2 divided by 2, and then plus M2 equals 0. And we can do some rearranging. I'm going to do some rearranging and do an algebra step all at once, and I'm going to get M2 is negative 0.1 x2 squared plus 0.5 x2. I encourage you to pause the video and do your own algebra here, just so you can see how I got to this final form of M2. And so these are our functions for the domain of x2. So we can write a summary here just to summarize our results. So on the domain from 0, x1, up to 5 feet, we had V1 equals 0.5 kips, and we had M1 equals, let's scroll back up and double check, 0.5 x1 minus 2.5, 0.5 x1 minus 2.5. Yep. And then on the domain 0 x2 up to 5 feet, we had V2 as negative 0.2 x2 plus 0.5, and M2 as negative 0.1 x2 squared plus 0.5 x2. And that concludes this example. If you like this video, please hit like and subscribe.